Okay, I wanted to go over exam one. Exam one, and I'm just going to focus on the problems. And the first one, I had 5 charges located on a circle, and I've drawn the 5 charges here in blue in this circle, and in purple, I've highlighted the x and y components of the electric field due to each of the charges. All the electric field vectors will point towards the center of the circle in this particular problem. But this problem can be a pain to do this way. What I can do is I can take this picture that I've drawn. I've drawn the location of the charges arbitrarily. I can rotate this thing counterclockwise by 60 degrees just for the analysis sake, and I just have this picture. So now I move this 60 degrees. This guy goes here, this guy goes down, this guy goes from here to here, etc. Okay, so this guy goes from 42 degrees below the x-axis, it goes to 18 degrees above the x-axis. And so I've drawn the electric field vectors in this picture in red, and the charges here are in purple. So this is 18 degrees, that's 18 degrees. These are all equidistant from the center, even though my picture doesn't show that. But if you look at this x component and this x component, these two are basically an e cosine 18 term, but they're in opposite directions, so they cancel. These two components, due to these two charges in the x direction, they're both 54 degrees below the x-axis. Again, they're all equidistant from the center of the circle. They're going to cancel out too. So the x components cancel. And now we're just left with the y components. So the y components, if we look at them, we have one pointing down. And I want to let k, q over r squared be equal to the magnitude of the field due to one of the charges. Of course, all the magnitudes are the same, and let me call this just E naught. So basically, if I look at this, I have E naught pointing down. I have these two y components are going to be upward. There's 2 of them. And then these 2 are pointing down. And I got to figure out what this comes out. And it turns out that this ends up being 0. So E sub y is 0. And so the field at that point is 0. And whatever charge I put here at the origin is not going to move, because there's no field there. And remember, the force on a charge that you place at the origin can be determined by Q times Z. Well, Q times 0 is 0, so it ain't going to move. So in part B, it ain't going to move. Okay? All right. Let's look at problem number 2 on the exam. And I thought that for problem number 2, the second part, to me, was probably the hardest part of the exam. In the first part, all we got to do is find the electric field due to a non-uniformly charged sphere everywhere inside and outside the sphere. Since I'm going to need to use Gauss's law, I need to figure out Q enclosed, whether it's somewhere inside the sphere, okay, or I need to find a total charge. Q enclosed for this sphere of density A r cubed can be determined by the integral of rho dv. My limits of integration depend on whether I'm doing the problem inside or outside the sphere. If I'm doing the integration inside the sphere, since my charge density depends radially, then my dv is going to be 4 pi r squared dr. And I'm going to use a dummy variable. Okay. And when I evaluate this, I'm going to get, well, let me take out some terms. 4 pi a, and then the integral from 0 to r. And this is going to give me 2 over 3 pi a r to the 6th. That's Q enclosed, and I wrote it as a function of r because if I'm inside the sphere, I'm going to use little r. But if I do the integration outside the sphere, then I'm just looking at the total charge on the sphere. So let's do this problem for calculating the field. Remember, this is based on homework 1, problem 9. I'm going to draw the sphere again. And my Gaussian surface is inside. That's my Gaussian surface. So I'm going to take the integral of E dot n dA, and that's going to be Q enclosed over epsilon naught. Well, we know that the electric field is going to be everywhere along here perpendicular to the surface. It's going to be radially outward. And so I'm going to be able to pull this out of the integral. And E dot n just gives me E because the normal to the surface and E are parallel to each other. So dA is just 4 pi r squared. And Q enclosed is just given by that equation. These pi's cancel. And then if I solve this for E, I'm going to get A over epsilon naught. I'm going to cancel out 2 r's, r to the 4th, and then I'm going to have a 6 in the denominator. That's going to be for r less than or equal to big R. Now, if I want to go outside the sphere, I want to calculate the electric field outside the sphere. You should know the answer already. The answer should depend on 1 over r squared. Because once you're outside the sphere, you basically have a point charge. And it's the matter of determining what the total charge is of the point charge. So let's go outside the sphere. Here's my Gaussian surface. That should be concentric. There's my arbitrary radius r. I'm going to use the same prescription here. E times 4 pi r squared comes from this. And then my Q enclosed is going to be my total charge. Everything that's in charge inside this blue thing. So my R then in my equation here is going to be big R. And then when you solve this for E, what you'll get is A r to the sixth over 6 epsilon naught r squared. Okay? And this is for r greater than or equal to big R. Now, part B was the hard part. Part B, what you had to do is calculate the flux through a disk that's inside the sphere. And this was the hard problem. So I only made it worth 8 points. You just had to set it up. So let me try to draw a picture as best as I can. Here's a sphere. And I'm going to choose a ring of radius B. Well, not a ring, a disk. I want to find the flux through the disk. That disk that's blue. Okay, now I got to be careful with my letters, okay? Now, my electric field as it approaches the disk comes at an angle with respect to the disk. I want E dot N. The normal to that disk points straight down. Let's call this angle theta. And this angle theta. You can see that you want the Z component of the electric field. That dot product gives you E sub Z. The dot product is the component perpendicular to the surface, anywhere along this disk. That's E sub Z. But you notice that the normal point's opposite the direction of the electric field, and so this is going to be minus E sub Z. Because the angle between the two vectors, N and E, you actually got to put the two tails together to get the angle between them. That angle is going to be bigger than 90, so that's a minus sign. Okay, so I need to write down then E sub Z. I need the Z component of the field inside. I'm sorry, right here. So that's going to be but I got to be careful what this R is. The R is the distance from here to here. So how am I going to enumerate this? I know this distance is given. Right? My distance that I've given is B. So this disk is a distance B above the ring. I'm sorry, above the origin. So this distance is B. So when I look at this, I have a distance B here. And then I have this distance, which I'm going to have to figure out what that is. I'm going to call it by the Greek letter rho. And I'll show you what I mean by that. So this distance R, the distance from here to here, is not R to the fourth, but it's the square root of rho squared plus B squared. and cosine theta. And that's going to give me the z component. Okay. Now, what's cosine theta? It's going to be b over rho squared plus b squared to the 1/2. So that's E sub z. Now where does this rho come from? Okay, so I have to integrate over an area. I have to integrate over this area. So I have to divvy this up into a, somehow, I'm going to divvy it up into a bunch of rings. Okay, so we're going to divvy up into a bunch of rings. dA of the ring is going to be 2 pi rho d rho. So when I set up this integral, I forgot to put that there before. Okay, when I set up the integral for this problem, I don't want the flux through a closed surface, I just want the flux through a disk. I'm going to calculate the integral of the z component of the electric field times my dA, which is the integral of this thing and the numerator is just going to be rho squared plus b squared squared. And then my dA is 2 pi rho d rho. And my integral from 0 to b. When I simplify this, I'm going to get the following. Two pi a b over 6 epsilon naught times the integral from 0 to b. And that's going to give me my flux through that blue disk. Okay, so that was a little bit more challenging problem. All right. Okay, the next question, and most people set this up, most people were able to sum of this up, they weren't able to figure this out. Some people actually did, to write R in terms of this, in this form. Okay, so some people got close. Some people were able to set it up, but they just didn't write the R correctly. Okay, so there are some people who came close to this one. So the next problem is an electric field problem. We have a vertical rod along the y-axis. So let me draw the vertical rod. It's drawn symmetrically about the x-axis. And you want to find a point, the electric field, at some point P over here, where this coordinate is A0. And you're given that the charge density, lambda, is equal to y squared plus a squared to the 3/2. And you might wonder about the dimensions of this thing, but you know, there's a number 1 in front of it, and then number 1 can have whatever dimensions required to make this thing work out. Okay. All right, so Basically, you're trying to follow procedure. And so what you need to do is to break this thing up into a bunch of DQs. Okay? You need to break this up into a bunch of DQs. Along the y-axis. So this distance here is y. And so dq is lambda dy, which is equal to y squared plus a squared to the 3/2 dy. So I have that. Now, when I take a look at the electric field is going to point from here to here. It's going to point this way. And then below the axis, if you draw the electric field vector, it's going to point this way. You will see that the y components will cancel. And only the x components are not zero. So the only component of r hat that I need is along the x direction. So if I denote this as the angle theta, then I just need cosine theta, okay, for the x direction, and that is going to be basically a over the square root of y squared plus a squared. Okay. Now the other term that I need is my r squared. That's just going to be the hypotenuse squared of that triangle. And so that's going to be y squared plus a squared. So now I just put this all together. dE is k dq over r squared times cosine of theta. And you can see the math gets real simple. I'm going to integrate from 0 to a, from minus L to L, So I'm going to integrate k times a. I'm going to have k times a times the integral from minus L to L of dy. And by the way, one thing I forgot to do is put the unit vector. And so this comes out to be 2k al in the I hat direction. Okay. Then I know the units look weird. That's because you don't see the units on lambda. But you know, there's a 1 in front of it. That 1 can have whatever units needed. Okay. So that this comes out to the correct number, the correct units. Okay, so that's how you find E. All right, the electric field's in the x direction. Now, the next question says, what is the electrical potential if you have an odd function representing lambda? If lambda is odd function, what can you say about the electric potential at point P? Well, first of all, my V is going to be the integral from minus L to L of K lambda dy. And then in the denominator, I'm going to have the square root of y squared plus a squared. And this is going to be the whether this function is even or odd is going to be determined by what lambda is. Okay. So if lambda is odd, you're going to be integrating an odd function over a symmetric interval. In other words, you're gonna be integrating something like this, or you're gonna be integrating something like this. If you integrate an odd function over a symmetric integral, you're gonna get 0. And I don't want to do this proof formally, but an odd function is something such that f of minus x equals minus f of x. If I integrate a function from minus a to a, I can break that up into two integrals. The integral from minus a to 0 plus the integral from 0 to a but if I replace x with minus x, then this is going to end up being the negative of this one. And I'm going to get 0. Now, another way to look at it is, how much charge is this? If this function's odd, how much charge is in this rod? This rod has no charge. Remember, this is a scalar. Okay? This thing has no charge. Q is 0. So why should the potential be non-zero there, right? If my total charge is 0, this charge distribution, the total charge is 0, then my potential at that point is going to be 0. Doesn't mean the field's 0 at that point. All it says is that the potential is 0. Okay, because we're symmetric about this point. We're symmetrically above and below this point, so this point's going to see no charge. Okay. So those are a couple of ways to see that. Some people kept referring to electric field, and the question did not really refer to the electric field. Problem 4. And problem 4, basically you had a particle in a potential V equals 9.80 or 9.8 times 10 to the 4th volts. I'm sorry. You have an electric field that depends on the y direction. If I take the derivative of this, I'm going to get the electric field, because if V varies in the y direction like this, then I know I have an electric field. The electric field is going to be minus dV over dy, and it's going to give me minus 98,000 in the j direction. Well, the net force on this thing is going to be in the y direction. The net force on this is going to be in the y direction. And of course, the net force is Q times Z, which is M times A. A is going to be Q E over M. And this is where I made my mistake in the problem. I chose the wrong values of Q and M. Okay. I chose the wrong values of Q and M. I was trying to make A become minus 9.8, but I chose the wrong values. So, let me find my values. A ends up being the mass 1.6 times 10 to the minus 21 kilograms. 1.6 times 10 to the minus 17 coulombs. And then minus 9.8 times 10 to the 4th volts per meter in the j direction. And in fact, I made such a bad mistake that when you calculate the velocity, you really get an unphysical result. I'm breaking the laws of physics, and I didn't catch that. So this comes out to be 9.80 or minus 9.80 times 10 to the 8th meters per second squared in the j hat direction. And so since A is dv dt, then dv is a dt. And so basically I integrate both sides. V is going to be equal to this guy plus V initial. Well, V initial is in the x direction. That was it. Okay. The problem is after 2 seconds, this thing, actually after 1 second, it's relativistic. It's beyond the speed of light. Okay. So when I asked the question in part B, I noticed a mistake in my. It was too late. I noticed a mistake in my my math. I got you get an answer that's really non-physical because it's going to be going faster than the speed of light. Okay, so that's my bad. But anyway, if you proceed in this problem, in part B, you have to calculate the displacement. dr over dt is V, then dr is v dt, and delta r is equal to the integral of v dt. Delta r is r minus the constant of integration. Okay? Basically, that's what it is. Okay? It's r minus r initial. And so this is going to be basically I just have to integrate this, and I'm going to get minus 4.9 times 10 to the 8th meters per second squared times t squared j hat plus v naught t I hat. And I evaluate it from 0 to 2. Okay. And that's it for that one. If you actually plug in the time, you get not really a nonsense answer. So that was my bad. I didn't check. I wasn't careful with the numbers. Okay, the last one looks hard, but it's really not. To me, it's very conceptual problem. So let me go through the last one. In the last one, we have a sphere. And a wire. So the sphere is at x equals r. First question I ask, what's the total charge on the sphere? I just have to integrate to get the total charge. So the charge density is AR squared. So the total charge, I got to integrate the density over the entire sphere. Since this thing depends radially, the volume elements will be 4 pi r squared dr, just like we said in the first homework assignment, problem 9. When you integrate this is a straightforward integral. You're going to integrate r to the 4th. You'll get 4 pi a r to the 5th, big R to the 5th over 5. That's the total charge. Part B, If I put a charge at 3r, a little charge here, what force is this thing going to experience? Well, this guy is going to experience a field, so the force is going to be Q times electric field. And I just want the magnitude of the force. So I just want this. But what is the field at that point? It's going to be the field due to the sphere minus this field due to the wire. How do I know that? Well, draw a free body diagram. This is positive, that's positive, that's positive. Isn't it true that Q is going to be repelled from this guy? So there's going to be a force in that direction due to the sphere. And then these two are positive. There's going to be a force in that direction due to the wire. This is going to be Q times electric field due to the sphere. This is going to be Q times the electric field due to the wire. Since you're outside the sphere, the electric field due to the sphere is just K, Q, and then the distance from here to here is just going to be 2R. And the distance from here to here is just going to be 2R. And the field due to a wire is going to be K, 2K lambda over R. Now I gotta substitute my Q in there, my value for Q in there, which is 4 pi A R to the 5th Okay, that's it. That's my answer. I don't have to, you don't have to simplify it anymore. But so the problem is very conceptual. Even the last question is very conceptual. So I want to find the electric potential difference between 3R and 4R. I want V at 4R minus V at 3R. So I need to find the potential due to the sphere plus the potential due to the wire. So for the sphere, I'm going to integrate from 3R to 4R, K, Q, and I'll put the Q in later, over R squared dr. Actually, I'm sorry, it's not 3R to 4. The distance from here to 3R is 2R, so it's from 2R to 3R, sorry. Because my origins are over here. Okay. All right, the distance from, we're going from here, this distance is 2R and this distance is 3R. So I got to go from 2R to 3R. So this is the potential difference due to the sphere between 3R and 4R. But then I got to integrate the electric field due to the wire from 3R to 4R. But in terms of this, in terms of the distance we are from this wire, you're going from R to 2R. This distance is R, this distance is 2R. So we're going to be moving in that direction. All right, we're going from here to here. So we're going to start from further away and then get closer. So I'm going to set up the integral in that fashion. Now this is tricky, and I didn't grade this part. For this sphere, if I integrate in that direction, my dr is negative. Okay, my dr is negative when I integrate that direction, this term. And so really I have to throw in a minus sign here. And so now it's just a matter of just integrating this. This is easy. This is natural log. All right, this term is just natural log of r over 2r. And if you're going in this direction, you're going against the direction of the electric field, the electric potential has to increase. Okay, so this means that this whole thing becomes a positive number, which it does. But if I don't take this into account, that doesn't happen. So this is the tricky part. So this part becomes 2k lambda natural log of 2. And then this term becomes kq times 1 over 3r minus 1 over 2r. And this is negative because if you're going to the right, that charge is positive, the potential will decrease. Okay? And then you can substitute the value for q in there, and then you can simplify this if you want. But that's your delta v. So this was a little bit tricky, but really what I was looking for is, can you set this up? Those little details I really wasn't, if you got this detail wrong, I actually wouldn't take off point for that. Okay, I was looking, can you set this up? And you didn't have to simplify it all the way down. Because I realized, there's a time limit. Even this, I didn't expect you to simplify it. I just expect you to make a substitution. All right. Just because, again, there's a time limit on the exam. As long as you know how to set it up, that's really what I was looking for. Okay. And except for this one, this was kind of tricky, so I didn't really I didn't take off any points if you had that wrong. Okay, well, that's it.